Again. Okay, welcome to the third lesson. Thanks for all joining. So, does anyone wants to answer this warm-up question? What is supervised and what is unsupervised learning? This is from lesson 2. You can unmute and answer.
Unsupervised is unlabeled data, whereas supervised is labeled data fed to a model.
Got it. And what about root mean squared error? Yeah, Amir, go ahead if you want to answer.
If I remember correctly, root mean squared error is we sum all the errors. So for every data point, there is an error between what the data actually is and what we predicted it would be. For example, in a linear model, it would be like y equals ax plus b. So we have some error. We sum all the errors to the power of 2. The reason we do that is because we don't want negative errors to remove the effect of positive errors. We want to have a way to quantify the absolute amount of errors. So so that's what we do. And then when we sum all of them, the unit that we have is actually the unit of the data we have to the power of 2. So we take the square root of that in order to have the same unit that the other data that we have also uses. So for example, if we have grades of students from 1 to 20, and then we have a root mean squared error of, let's say, 3, well, that means that for a given data point, we are expected to fall between plus minus 3 grades from the expected value.
Okay. I think how do you classify a model as a best model based out of root mean squared error? Um, if the root mean squared error is close to 0, then the model is performing best.
No, not necessarily. Um, I think there is a very good balance that we can have with
Mm-hmm.
how much we use in the test data versus the training data. So if it's 100% matching, maybe we're overfitting it,
Mm-hmm.
and maybe we're giving the model too many um, degrees of freedom, and then it just matches the data perfectly, but it's just so localized. Instead, if we have like a model with fewer degrees of freedom, it may have more, like a bigger root mean squared error, but it is more capable in predicting higher ranges of data that we may not necessarily have in our data set.
Okay. Yeah. So what I know is if the root mean squared error is close to 0, then the model is the perfect model. But you can, yeah, try to print root mean squared error for the model you train as part of your assignment and check what's the value for that. So you get better understanding. Okay. Yeah. Let's thank you for answering those questions. Let's start with lesson 3. In lesson 3, we'll be discussing about data preprocessing and feature engineering. In that, we discuss about how do we scale the numerical features and how to scale or encode the categorical features, and then we'll look at principal component analysis, and then In the last lesson, we looked at how to evaluate a linear regression model, which is by using root mean squared error and R2 score. Today, we'll look at how to evaluate a classifier, a classification model. And we'll look at k nearest neighbor classification model and a logistic regression model. So this is the agenda for today. So let me yes, let me just I'm trying to open the presentation. Okay. So and you already know what is a classification. Classification is to predict between categories. Let's say you have an email, you want to classify the email as a spam or not a spam. Um, let's say you have a banking transaction, you want to classify it as a fraud versus legitimate transaction. So these are some of the examples the classification solves, right? So for classification also we use scikit-learn because classification is also like a classic machine learning technique. And as I said, we will look at KNN and logistic regression, right? So pre-processing. So your features, if you remember, if there are large numbers in your data set, in your feature, then there may be a chance of your model will be overfitting or underfitting. So pre-processing is actually important and necessary for before we train the model. So for numerical features, if your feature is basically if your data set is numbers, that is called a numerical feature. And for numerical features, there are two types of scalings. The first one is normalization. The second technique is standardization. So normalization is min-max scaling. You rescale your features so that it will fit in the range of 0 to 1. So this is min-max scalar. And standard scalar is where it is called jet score normalization. It'll okay, which transforms your numerical features so that its mean becomes 0 and standard deviation becomes 1. So this is standardization or jet scale normalization. So when scaling matters, KNN is an k nearest neighbor technique. So when you're doing nearest neighbor technique, you are trying to predict the value based on the distance. So you have to apply scaling here. And this is an example code for standard scalar. You were importing min-max scalar from sklearn.preprocessing module, and you're creating the scalar. You're trying to apply fit underscore transform on your trained data set. Yeah, this is how you apply a standard scalar, right? Similarly, it's a similar with jet scale also. You can check the code for jet scale, right? And encoding the categorical features you need to encode, because in order to train the model, the features should be in numbers. You cannot train the model on strings, right? So you need to encode your your strings such a way that the machine can understand while doing while doing machine learning, right? So so here is one example of encoding. You Let's say your data has cat, dog, and tortoise. Then for cat you put 1, and for others you keep 0, 0. And for dog you put the middle value 1 and other value 0. So this is how you encode and transform your data for categorical features, right? So that is about pre-processing and encoding. And I think we talked a little bit about feature engineering. Feature engineering is where you create new features from the existing features, right? Examples can be, let's say you have a height and weight columns in your data set, but you don't have BMI column in your data set. But you can compute BMI from height and weight and add that as a feature to your data set, and you can train your model on BMI feature as well. So that is one example of a feature engineering. And another example is, let's say you have a timestamp which includes day, month, year, but you want to extract only the year from the timestamp and you want to keep it as one feature. So that is one example of feature engineering. So so here is an example of a data frame which has weight, height, and age, and you are creating BMI feature based out of weight and height. Um, and binning binning is one kind of a feature engineering. Let's say you have age in your data set, but the actual age of each person is not important for you in order to train the model. Instead, you want to categorize them into 2 or 3 categories. So these are categories here, the labels you see. Um, if the person's age is less than 20, you want to categorize as young. 20 to 30, you want to categorize as 20s. 30 to 40, you want to categorize as 40s. And above 40, you want to categorize as 40 plus. And now this becomes your new feature. So this is how you apply binning. Out of your data set, you were kind of segregating them into certain group based on their age. That's an example of a binning technique. And this is the code to do the binning. You tell the bins and labels. So, and one other way to create a feature is, let's say based on age, you want to say the person is senior or not. It's a Boolean feature. If the age is greater than 65, you say is senior true, right? This is one more feature. So these are some of the examples of creating new features or feature engineering. Okay. Why do we have to create features? I think by now you already know. Um, in order to train the model on the correct data set, it is required to create new features or require feature engineering. And dimensionality reduction, I think we spoke about this a bit in the ML intro lesson. So dimensionality reduction is actually you are reducing the number of features and then training your model on the reduced number of features. Let's say you have 1 million features. You don't want to train your model on 1 million features. Instead, you want to train the model on 3 features, but you get the same performance in predicting the values, right? So this is basically about principal component analysis. So in PCA, where is it required actually? So many real data sets have correlated features, right? There may be 1 million features, but all of the features are correlated, right? They have a positive linear relationship. Then you really don't require 1 million features, right? You require one feature if all the features are positively correlated. So in principal component analysis, you are basically saying how many components you wanted out of the total number of features you have, right? Here I'm saying I want 4 features or 4 components out of the total features. Then you are trying to check each component's variance. If you see here, the PC1 is basically covering 98.31 percentage of variance of your data set. And PC2 is covering 1.52. If you just add PC1 and PC2, you are covering 99.8 percentage of the variance of your data set. You are just leaving behind 0.02% of the data set, right? So, um, yeah, here, so this is an example of reducing from 1 million features to just 2 signals, and you get the same performance. So, um, and here is the code for principal component analysis. You were saying how many components required, and then you were applying transform. So yeah, this is about principal component analysis and how we will evaluate a classifier. So we have a confusion matrix to evaluate a classifier. Let's say you have performed COVID test on 100 patients. 30 patients are positive, 70 are negative, COVID positive, COVID negative. Then let's say you used your model on those 100 patients, right? And this is your model output, right? So actual 24 people are actually COVID positive and your model predicted as COVID positive. That is true positive. It's actually positive and the prediction is also positive. So that is true positive. And 6 people are actually positive, but the model predicted negative. So that's a false negative. Model predicted negative, it is actually positive. So that is false positive. Sorry, false negative. Okay. So, and here it's 10 people are actually negative, but the model predicted as positive. So this is false positive. And 60 people are negative actually, and the model predicted negative. So this is true negative. So, so if you see out of 30 patients who have COVID positive, your model predicted 24 patients right and 6 patients wrong. And out of 70 patients who have COVID negative, your model predicted 10 wrong and 60 right. So that's how we have to interpret this confusion matrix, right? I think this is the same thing. And so once you have confusion matrix, you basically check the accuracy. To evaluate a classification model, you have these 4 parameters to check for model's performance: accuracy, precision, recall, and F1 score. So accuracy is true positive plus true negative divided by total samples. That means it is actually telling how many true or correct predictions the model is making. In this case, it's 84%. Because this is true prediction and 24 is true prediction. 60 plus 24 is 84. 84 is the true prediction. So 84% is the accuracy. So precision is true positive divided by true positive plus false positive. It actually tells when the model says positive, do we really have to trust it? So this is about precision. So let me switch over. So precision focuses on cases when the test says someone has COVID. Um, yeah, So a test with lower precision produces many false positives, which can cause unnecessary worry, right? So your precision for your model should be high. If the precision is low, then your model is making wrong predictions. And um, recall is how trustworthy the test is, right? Um, if someone has COVID, how likely is the test to actually detect it? How sensitive is the test to actual cases of COVID? So this is what we try to find out in recall. So in our case, the recall is 80%. Um, and F1 score is basically a balanced metric between precision and recall. If you just go with the prediction, it's not always guaranteed that your model is really performing well. So it's best to check F1 score rather than precision and recall. So F1 score is a balanced metric between precision and recall. So one example where your precision may be high, but the model may not be predicting well is where if your data set is only having 2 out of 100 people COVID positive, 98% of the time, 98% of the patients in your data set are COVID negative and only 2% are COVID positive, let's say. And your model might be randomly predicting everybody as COVID negative. It's not actually or correctly predicting, it's randomly predicting as COVID negative, but your accuracy score will be high because your data set has 98% COVID negatives. So in this scenario, if you go with only precision, you cannot guarantee that your model is really performing well, right? So that is one example where you need to actually check the F1 score. So this is the formula of F1 score. For a good model, F1 score should be close to 100. So for a good model, accuracy should be high, precision and recall, F1 score, everything should be high. So, so any questions on the confusion matrix evaluation? Okay, yeah, please type in your questions. We will try to address them at the end. So, yeah, so the next concept is K nearest neighbor classification technique. So let's say you have this data and you want to predict this particular object if it belongs to category blue or category red. Then, and we are trying to apply K nearest neighbor technique here, right? So if you're saying K is 1, your model tries to look for one nearest neighbor for the value it has to predict. And here the nearest neighbor, one nearest neighbor is red color. So your model will predict this object as red color object. And let's say you were taking K equals to 3, then your model will look at 3 nearest neighbors. And you can see in this picture, 2 of the neighbors are blue color, one neighbor is red color. So your model will predict it as a blue color. If K equals to 4, your model don't know how to predict it. If there is a tie between the blue and red, so it's suggested to take odd number for K. And so this is the concept of K nearest neighbor, right? So here is the code. You were splitting your data set as train and test, then creating a K neighbors classifier. We are taking K as 5 here. So it look at 5 nearest neighbors in order to predict. And then we are applying fit. After that, we are predicting on the test set, right? And we are printing classification report. We look at precision recall F1 score to understand the evaluation of the model. So here, for K nearest neighbor, you require scaling because it's distance based. And if you have small k, then it may be sensitive to noise. If you have large k, it may be underfit. Then now the question comes is how to choose k, whether it should be 1, 3, 5, or 11 or 7. So how do we choose k in order to train the classification model is the question. So so to choose k, we have to apply cross validation technique. So cross validation is where your training data, you split your training data. Let's say in this diagram, we are splitting the training data into 4 folds, and one fold you are using for testing, 3 folds you are using for training. And you need to do that for 4 times. Every time you change the test set. For the first time, I took the fourth fold as a test set. For the second iteration, I took the third fold as the test set, and I'm training on the remaining folds. Let's say on the fourth fold, let's say n equals to 4 here. On the fourth fold, you're taking the first fold as a test set and the remaining folds for training. And then you do this with k equals to 1. You find out the mean, average mean, and you change the k to 3. Again, do all the folds. You calculate the average mean, and you continue this process and find out the best k, right? So think
Ask a question.
yeah.
You said we iterate until we find the best k. What is the best k? How do we distinguish the best k?
Yeah, so that is what I'm trying to show. I was asking that question. So you're calculating the average mean, right? And um yeah, let's see. So so we need to take a k where it minimizes the mean and maximizes the accuracy, minimizes the mean error and maximizes the accuracy. So let's see here. Yeah, we are printing the mean here. Let's ask the range also. I forgot. I was checking just before the class. Range for mean CB error. So yeah, I think error rate is 0 to 100. If your mean is very near to 0, that is the K you need to take. Does that clarify your question?
Yes, thank you.
Okay, thanks. Great question though. So that is about KNN. Once you have the K, then you actually use that K to train the model, right? So So here you can see we are in the for loop, we are choosing different k values and then trying to print mean. And once you, in this example, best k is identified as 5, and then we are using the best k and then training the model on the actual data. And now we verify on the actual test data we have. We have test train split, right? Here in this case, we divide the training data only. We don't expose the test data. We divide the training data into multiple folds and then try to find the k. Um, so I think I'm moving on. That is about KNN. Logistic regression. So yeah, please type in your question in the chat. I'll try to answer in the end. Okay. So the logistic regression, um, so here we are in terms of in classification, we are trying to predict between categories, right? Let's say you want to predict between cat and dog, then your model output should be a probability in order to classify as class 1 or class 0, in our example, as dog or cat. So, so the output you get in logistic regression should be between 0 and 1. So for linear, think of this as like linear regression, but at the end you apply a sigmoid function to map the output between 0 and 1, right? So that is how to visualize the logistic regression, right? Um, so so if you see here, it's more the formula is the same. Wx plus Br, B0 plus B1 into feature 1 plus B2 into feature 2. But you, at the end, you get a number like -5 plus 7, etc. is your model predicted value. Then you apply sigmoid function to get the value between 0 and 1, right? So this is about logistic regression, and the code is actually simple and similar to other models we saw. We we take train test split, then we are applying feature scaling here. Once we apply feature scaling, we are taking a logistic regression model and trying to fit on the data, right? So if we have multiple features, it's the same thing. You you do scaling, take a logistic regression model object, then apply fit, right? So that is logistic regression. Um, and yeah, here we have printed accuracy and F1 score for logistic regression. Accuracy is 92%, F1 score is 91. Um, so so there is a concept of regularization for logistic regression model. This is to prevent overfitting. For that, there is a C to prevent overfitting or to regularize the model. So so let me see. So okay, let's switch over here. I'm trying to explain about coefficient C. Actually, C is cross validation. So you do cross validation and you find out C, but you set the C to the model uh, in order to prevent it from overfitting, right? So okay, let's read this. So here we are passing C as 1. So C parameter controls something called regularization, right? Regularization discourages the model from assigning very large weights to individual features. So we know our model formula is Wx plus B or W1x1 plus W2x2 plus B. Here W1 and W2 are weights. So the C you supply basically controls the weights, meaning the W, right? So if your weight is too big, then it may overfit, right? For one feature, if the weight is very big, then it may overfit. So that's why you need to pass the C in order to prevent overfitting. How do you pass the C? That is called again cross validation on C, it seems. So you can explore this concept further, right? So a small C applies heavy regularization, pushing all your weights to zero. A large C applies almost none. So it says C equals to 1 is the default and reasonable starting point, which is why we set it to 1. So yeah, you need to tune C with cross validation. So you can learn about this further by yourself. I think that concludes the session. So we discussed about pre-processing, scaling of numerical features, and encoding of categorical features. We discussed about principal component analysis, reducing the signals from 1 million to 2 signals, but without losing the model performance. We discussed about confusion metrics. You need to check for precision, accuracy, recall, FN score in order to evaluate your model. We looked at KNN, how to find K with cross validation as well. We looked at logistic regression and regularizing by using C, right? So the next session is applied ML. So we'll look at applied ML in the next session. Thanks for joining. I'll stop the recording.